Okay, so I forgot to mention and compare the two cases that we just got done doing in terms of answers. So the simplified method that we just did gave us these answers. So in other words, at 1 year I got 0.131. The more complex method, the first way, I got 0.106. At 5 years, 0.36, 0.41. 20 years, 0.596, 0.622. So both methods are close. The simplified method only works for the case where we have a fill. If we have a building, we cannot do this simplified method. So we're going to concentrate primarily on the more difficult method where we are using the curves. In other words, we are going to be using these curves most of the time. We are not going to be using this curve very much, simply because this curve only applies in a certain specific situation. All right, so one other comment I want to make about this is that typically we'll make a plot of delta H versus time. And when we do these plots, we always have 0 delta H at the top. So that's just the way it's always done. And delta H increases in the downward direction. Now, I'm just going to let you know that, okay, so we have time here, and then you just plot, okay, at 1 year the settlement's that much, at 2 years the settlement's that much, at 3 years the settlement's that much, and then you just connect it with a line. Just to let you know that when you're in practice, you have to be very careful, because I plotted the same data twice here. If I look at this curve, you'd say, oh, we're almost done with settlement. But if I plot that same data to a different time scale, it looks like this. And you'd say, oh, the final settlement's going to be way down here someplace. So, as I said, these are the same plots, but to a different time scale. And this is very deceptive. Why is it deceptive? Because for the top plot, we say that settlement is nearly finished. But for the bottom plot, it looks like there's lots of settlement left. So what is the conclusion here? Don't make conclusions with this type of plot. You have to look at it. You have to look at the excess pore pressure, really. Because one thing we know is when the excess pore pressure goes to 0, then settlement's pretty much over. So I'll just say it's very difficult to make conclusions from this type of time rate of settlement plot, because you don't know what to use for the scale of the time. Okay. This is a little bit of a review, so let's just remember we had to find the point of interest H and Z sub f for our building. So why don't you take a moment. So here's our, I guess it's not labeled here, but this is our T equals 0 minus, and this is our T equals 0 plus 2 infinity situation. So why don't you pause the video, find the depth to the point of interest, the depth to the point of interest, the H and the Z sub f for this situation. Okay, I've assumed that you've paused the video. I'll just give you the answer. We've done this problem. What do we do to find the point of interest? we first draw the pressure bulb, which is 2 times the width. So it's 80 feet because the width is 40 feet. That means that the pressure bulb goes down 80 feet 2 times. We find the bottom of the pressure bulb, which is 90 feet. The top of the clay, which is at 15 feet. And we take 90 plus 15 over 2. We get 52.5 for the point of interest depth. And our H is 90 minus 15, 75 feet. That means what? That means that the whole width, remember the H means what? This is the region that the clay is going to get compressed. Notice that this is a very deep, it's a very deep clay layer. See, 195, and you know, our basement depth is 10 feet. So it's a very deep clay. So that's why we have to do this. We don't have shallow clay. And we have our building, which, you know, as we know, the building only has a certain range that of stress influence. So, oh, and then the Z sub F, I forgot to do that one, yeah. So the point of interest depth is 52.5. The basement depth is 10. So 52.5 minus the basement depth 10 is 42.5. That is our Z sub F. Okay, do another one then. Why don't you pause the video? And again, for this particular situation, find the point of interest, H, and Z sub F. Just simply, it's just different geometry, that's all. Okay, I'm assuming that you paused the video, and the answers are these. Again, we note that B is 8 meters. The depth is 6, or the pressure bulb goes down 16 meters from the basement, which takes us to 18 meters. So again, the main thing that we're interested in is the bottom of the pressure bulb and the top of the clay. The bottom of the pressure bulb is at 18. The top of the clay is at 5. So our answers are 18 plus 5 over 2 gives us the point of interest depth. 18 minus 5 gives us 13 meters. And then the Z sub F is the point of interest depth minus the foundation base depth. We get 9.5 meters. Okay, so now what we want to do is put all this stuff together to get the time rate of settlement for a building. Now so our goal here in this one is find the settlement beneath the center edge and corner at 10 years and 25 years and infinity. Now, remember, to do our time rate, we have to decide whether the situation is single or double drainage. Now, looking at it, this looks like a double drainage situation. Why? Because at the top of the clay layer I have gravel. At the bottom of the clay layer I have sand. That sounds like double drainage. The problem is that we can't call it double drainage because what happens is that the region that we are stressing, the bottom of that is really only 18 meters. It doesn't go all the way through. So even though this looks like a double drainage situation, this is really single drainage because um, because the region that we're really stressing is way up here. It's not near the bottom sand. So it ends up to be a single drainage situation. So that the numbers that we computed for our H, in the previous was H is 13 meters, that is going to be our HDR for this case. And, okay, so recognize that. So some of this is a little bit of a review. We've already done this. Okay, so the weight of our structure is 10,000 kilonewtons. We have all of our soil properties here. Yeah, we got our unit weights. Those are unit weights. Our C epsilon R, our C epsilon C. Our OCR is 1.15. Our C sub V is 4.2 square meters per year. So we have all the soil properties. Now when we do this, we set up a spreadsheet in this manner. So we have our depth of a point of interest. Well, the depth of the point of interest we already calculated is 11.5. That doesn't change. We have our times that we're interested in. We always do 0 minus, 0 plus, infinity, and then we do the in-between times. We were interested in 10 and 25. So we're doing the same times for each. So we have this, so in other words, this is the center, beneath the edge, beneath the corner of the building. Okay, so what we're going to do is, the first thing that we do is we convert our small t's to capital T's. How do we do that? We use our expression, capital T is equal to C sub VT over HDR squared. And thought I had. And we get that, let's see, do I have that? Okay, yeah, in the previous one I said that HDR equals H, because I didn't write it down here. So let me just add that. HDR equals H equals 13 meters. Okay, again, with all of these problems, the key is to getting the UXS. If you get the UXSs correct, you will easily solve the problem. So it's all about the UXS. Everything else is straightforward. So the first thing we have to get is what is the UXS at t equals 0 plus? Well, the UXS at t equals 0 plus, how do I get that? Well, excuse me, what I'm showing here is the pressure bulb. In other words, we've done this before, you've done it before, so you shouldn't have any trouble with it, is that I use the pressure bulb to get this initial excess pore pressure. I'm not going to go through it because by now you should know how to do this part of it. In other words, I'm below the center. We have our Z sub F, we have all those things. You have to read the pressure bulb diagram, and you get your pressure bulb factor of 0.27. I didn't mention the figuring out the Q. The Q, remember, we have to take the weight of the structure minus the weight of the soil removed over the area. So again, we have the weight of the structure is 10,000. We have a 2 meter basement. So we have the 10,000, the weight of the structure. This is the weight of the 2 meter basement soil. Notice our 21 is our unit weight of our gravel divided by the area. So we get a Q of 114.3. So we take our pressure bulb factor, 0.27, times the 114.3, we get a U excess at T equals 0 plus of 30.9. Then what happens is time goes, so that's we've done before. So we know the U excess is 0 at 0 minus, it's 0 at infinity, and we've already done previously getting the 30.9. Okay, so the new thing that we have to do is get the U excesses at intermediate times. How do we get those? Well, now we're going to use this shaped plot, the excess pore pressure plot. So what we do is we take our value of T, 0.25 for that case, 0.62 for that case, and get these coefficients, the 0.48 and the 0.18. So how do we do that? Again, we look at our plot. Again, this is single drainage, so we get rid of, since it's single drainage, we get rid of the bottom half. We are in the middle of the stressed region, so we're going to go in through here, and then what we do is we find our curves that we're going to use. I don't know, maybe and we pick off the values at the top here. So there they are, the 0.48 and the 0.18. And what do I multiply them by? The 30.9, because that's my original excess pore pressure. So it's 0.48 times 30.9, 0.18 times 30.9. That gives me the excess pore pressure at the different times. Okay, so what I want you to do is I want you to pause the video and repeat exactly what I just did, but do it for the edge of the structure. So do that, pause the video. Okay, I'm assuming that you've paused the video and you've filled in these values. And hopefully you got these numbers here. Okay, so let's go forward with the rest of this is very straightforward, so we're not going to dwell on the rest of the part of it. I'll talk about the corner later. I'm not going to talk about the corner right now. Okay, so we have the U water table. You can all get that. I get the U by adding the U excess plus U water table gives me the U. Then what? How do I get my sigma V? Well, again, I look at the correct picture for the correct time, right? So times T equals 0 minus, I look at the T equals 0 minus picture to get the sigma V. Same thing down here. These are equal. Why? Because the T equals 0 minus picture is the same in each case. So that number is always going to be the same. Then I get my sigma V prime. So the easiest way to do this without, like I say, without thinking too much about it, I get my sigma V prime. Then to fill it in, I fill in the next sigma V prime because it's the same. I get my sigma V at this location by adding the sigma V prime and the U. So I add the sigma V prime and U, I get that. So like I say, you're following the, you're here, step 2, step 3, step 4, step 5. So it's easiest to go in that order. So I get the 252.9 here for the at time t equals 0 plus. And what do I know? It's because the picture from t equals 0 plus to infinity is always the same. There it is. That doesn't change. All that means that that value is going to be the same everywhere. So it doesn't change. So I just take and I can fill in. I can fill in all of these values, 252.9, 252.9, 252.9. All of the u's have already been done. So then these numbers are simply sigma v minus u. So 252.9 minus 78.5. 252.9 minus 69.3. 252.9 minus 63.7. Beneath the edge is the same technique. So I'm not going to go through it, but it's the same methodology beneath the edge. What do we do with those values? We do exactly what we do with settlement. Otherwise, is that we create our curves, settlement curves looking like that. Our sigma prime p, well, our OCR is 1.15. So what does that mean for our, how do we get our sigma prime p? We take the 158.3 times 1.15. That gives us, so 1.15 times 158.3 gives us 182. So, like I say, I'm just focusing on the center and the edge. So I put 182 at the corner. And then what I do is I put on all of the other stresses. So when I look at the center, what do I see? I have these stresses I'm going to put on there. The 158.3 goes to the left, the 174.4 goes to the left, the 183.6 goes to the right of the 182, 189.2 goes to the right of 182. So all of those points can be shown on the plot. I do the same thing for these. If you notice, all of these values are less than 182. So that all of those points on our plot go to the left of 182. So all of those points are going to be to the left of 182. So once we have them, we can calculate our epsilon v. And we're going to use each, for the first one, I'm only going from there to there. So I only do 0.03 log 174.4 over 158.3. But now I'm going to 183.6. So 183.6 is there again. So that means I have to use both portions of the plot. We've done this enough times, so. And then the last one, 189.2, I have to use both portions of the plot. I get my epsilon v values. Same thing for the edge. I get my epsilon v values, and then we just get our delta H as H epsilon v. Those are our delta H's. That's how we got there.